Hello and welcome back to this Chem 141 video series. Today we're going to be talking about titrations. Okay, so just a basic overview of a titration to start off. A titration is essentially a mixing of acid and base. Okay, and if you're not already familiar, an acid is something that donates a proton. And a base is something that accepts a proton. So just a basic a formula reaction for how acids and bases react with one another is we have, let's just say we have HA plus B negative turns into HB plus A positive. Okay? Or A negative rather. So in this equation, this is the acid, this is the base, this is the conjugate acid because it's after the base has gained a proton, and this is the conjugate base because it's after the acid has lost a proton. All right. So in a titration, and you'll be doing something very similar to this in lab, you're essentially you have a known standard solution, which is in this burette here, and you have an unknown solution, okay? For the standard solution, you know what the molarity is, so it has known molarity. But for the unknown solution, you don't know what the molarity is, so it has unknown molarity. And essentially what you're doing to figure out what this unknown molarity is, you're slowly dripping in an amount of the standard solution until you reach what's called the equivalence point. And this is, looking at these pictures at the bottom here, this is before the equivalence point, this is at the equivalence point, and this is after the equivalence point. So you essentially have this little indicator dye in the unknown solution that will tell you when it's reached the equivalence point. And the equivalence point is just when you have equal moles of acid and base mixed together. Okay, and figuring that out will help you figure out what this unknown molarity is. So you're slowly going to be dripping in the known molarity solution into the unknown molarity solution until you reach that equivalence point. And then you're going to record the volume of the known molarity solution that it took to reach that point. And one solution has to be an acid, one solution has to be a base, but it doesn't really matter which one is which. But the unknown solution will always go on the bottom. But you could have an unknown acid, you could have an unknown base, but yeah, you always mix it with acid or base. You could do a titration with strong acids and strong bases, which you'll be doing in lab. But you could also have titrations of strong acids and weak bases, or strong bases and weak acids, and so on and so forth. But yeah, so the equivalence point, when the indicator changes color, that's when you have equal moles of acid and base. All right, so I've just got a problem here that I'd like for us to go over. If you'd like to take your time and do this problem yourself before I go through it, take this time to pause the video and work through the problem. And once you've done that, unpause it, and I'll show you the answer. Okay, I'll go ahead and get started here. So we have an NaOH solution that's used to peel potatoes. So the potatoes are soaked in sodium hydroxide, and then after they're soaked, you can easily spray off the peel rather than having to use a blade on every single potato. And that concentration of the NaOH solution is normally in the range of 3 to 6 molar. And we have a solution of sulfuric acid, and it's 0.5 molar, and there's 45.7 milliliters of it. okay? And then we're using that to neutralize a 20 milliliter sample of NaOH solution. So the first thing we need to figure out is what kind of acids and what kind of bases we're dealing with. Are they strong? Are they weak? What's going on? Well, and this is the part where you'll need to memorize what strong acids and strong bases are compared to weak acids and weak bases. You'll be told what you'll need to have to memorize. But here, this is a strong acid. Sulfuric acid is a strong acid. And NaOH is a strong base. Okay, so we've got that figured out. Next thing we need to do is figure out what's the unknown solution and what's the known solution. Well, for the sulfuric acid, we're given both the volume and the molarity. So we have known molarity. So this is the standard solution, sulfuric acid. And the NaOH is the unknown. So the goal here is to try to figure out what the molarity is of the NaOH solution. And the way that we're going to be doing that is using the M1 V1 equals M2 V2 equation. Okay? M represents molarity, V represents volume. And the 1s and 2s are for each of the different solutions. Okay? So you might be asking, why are we multiplying molarity times volume? Well, I already told you the equivalence point is the point at which the moles of acid equals the moles of base. And if you remember from our molarity equation, molarity equals moles divided by volume, you know that molarity multiplied by volume equals moles. So essentially what we're saying here is moles of solution 1 equals moles of solution 2 at the equivalence point. Okay, so this is how we're going to solve this. Let's just say the solution 1 is the acid and the solution 2 is the base, just to keep things straight. So the molarity of the acid is 0.5 molar. And the volume that we're using is 45.7 milliliters. Remember, we have to convert that into liters. All right. And that equals M2, which is what we're trying to calculate here. That's the molarity of the NaOH solution, multiplied by the volume of NaOH, which is 20 milliliters or 0.02 liters. All right. And there's one more thing we need to do, and this is something you always have to watch out for. Do you have a polyprotic acid or base? Because that's going to affect some things. So what I mean by that is, can your acid donate more than 1 proton per molecule, or can your base accept more than 1 proton per molecule? All right. So in this case, we actually do have an acid that can donate more than 1 proton per molecule. Sulfuric acid has 2 protons here, okay? And each of those protons can be given off. So it can donate 2 protons per molecule. So in order to account for that, we have to add in multiplied by 2 on the acid side. But for the base side, since it's just NaOH, we don't have to do that because NaOH can only accept 1 proton per molecule. Now, if it was, let's just say, barium hydroxide instead of sodium hydroxide, oops, I messed that up. Then in this situation, each molecule of barium hydroxide can accept 2 protons, in which case we'd have to multiply that side by 2. Okay. So doing this problem, I'm just going to multiply the numbers out here. We have, so this is going to be 0.0457 equals 0.02 M2. All right. So then we divide by 0.02 on both sides, and we get M2, the molarity of the sodium hydroxide solution, equals 2.285, which is pretty close to the 3 to 6 molar range that they gave us. So that's how you calculate that. Okay. All right. Thank you for watching.